Okay, so where we were left off in the last lecture, we were talking about exceptions, and in particular, I was talking about something called stack unwinding, but I want to get into more concretely what happens during the stack unwinding process. This is something that happens during exception handling. It's the process whereby destructors are invoked to make sure that all of the objects that reach the end of their lifetime due to the fact they're leaving blocks, exiting blocks in order to process an exception, make sure that the destructors get called. So I want to illustrate this by way of a simple code example. So what I have in this code example, we have this function func, which calls func2 on this line here, and then func2 in turn calls func3, passing argument is 0. So when func3 gets invoked here, it's getting passed in 0 for x, and that's checking if x is 0. If x is 0, it throws an exception. So this program is always going, or this function when it's invoked func1 will always result in an exception being thrown in func3. And basically what I want to do here is kind of walk through when things are getting created, when things are being destroyed, and sort of the mechanism of how this whole exception kind of handling process works. So to start out with, when we first call func, what's going to happen is we're going to hit this line first. So this is going to cause a string called Dave to be constructed with the value Dave. Then we enter into this try block. We're going to construct another object, which is called by, which has this string just with the value by. So we have two things constructed. Then we call func2. So we're going to jump down to this function. We're going to construct another string variable called world, which has the value world. Then we call func3, passing 0 as an argument. So x is going to be equal to 0. We're then going to construct another string. This one's called, the variable is called hello with the value hello. Then we go into this if statement because x is 0. And we're going to create another string variable called first, which has the value first, another string variable called second, which has the value second. Then finally we hit this throw. So once we hit this throw, what's going to happen is we're going to get violently ripped out of the block, the most enclosing block that we're in. So basically the kind of the most direct block we're in is the one between this brace bracket and this brace bracket. What's going to happen is any objects that are local to that block, because we're leaving that block, not through a normal path of execution, but due to an exception being thrown, because we're leaving this block, the destructors will be called for any local objects to that block. And destruction always happens in the reverse order of construction. So basically when we were in this block, the first thing that was constructed was the variable called first, and then second was constructed. So when we hit this line here, we're going to get ripped out of this block. When we leave this block, and it doesn't matter if there's any more code down below here after the throw statement inside this block, too bad, you don't execute it. Oh, it was doing some memory freeing that was important or releasing resources, too bad, you don't execute it. So it becomes very important to do any cleanup in destructors for this reason, because the only thing that you're guaranteed when you leave a block due to an exception being thrown is destructors will be called. So if there's other important code that you want to have happen, for example, maybe doing some cleanup, you're releasing some error happens, so that we want to release any buffers that are allocated by that function, release memory, release, maybe you're holding a mutex, you want to release the mutex so you don't cause a deadlock or something like that. This would have to be done in destructors because this is the only place that reliably you can count on would be invoked by the language when an exception is thrown. Anyway, there is no other code here, and there is no kind of resource issues in this case because we're not allocating memory, but if we were, we'd be leaking it. Anyway, so the first thing that's going to happen is that the variable second will be destroyed first because they're destroyed in the reversed order of construction. So this down here is kind of a running tally of things that are being destroyed. So second is going to have its destructor called first. And first will be destroyed next. So this is the next one that appears in our list of things being destroyed during the stack unwinding process. Then we get pulled out of this block and we go to the next kind of most enclosing block, which is between these brace brackets here, in other words, the block that corresponds to the actual function itself. When we do this, this variable was previously constructed, but it's going to reach the end of its lifetime because there's nothing to catch the exception, so we're going to keep propagating up the call chain. So before we leave this function altogether, this variable hello is going to have to be destroyed because we're going to basically leave the block, the function that it's defined in as a local variable. So hello gets destroyed next. Again, because there's nothing to catch the exception, we keep propagating sort of upward through the call chain, leaving more and more blocks. So here we're going to end up being kind of ripped out of this function, and we're going to go back to the place where the function was previously called, or func3 was called, which was this line here. We're not actually catching any exceptions here. There's not a try block. So basically what's going to happen, we're going to get ripped out of the function func2. this block is going to be exited through an exception. So when this block exits, we already constructed this variable world, so it has to be destroyed, because when we leave this block, it reaches the end of its lifetime, this variable, therefore it must be destroyed. So world's going to be destroyed next. So like in our running tally of what's been destroyed, this is the next thing on our list here. Again, because there's no try block, we get violently ripped out of this function here and exit and end up back to the place where we called func2, which is over here. But what's different here, now we're in a try block. So what happens is we violently get ripped out of this try block. So any local objects that are local to this block will get destroyed. So there was one, by. So by is going to get destroyed. So this, we add this to our list here of things being destroyed down at the bottom. But what's different here is that when we get pulled out of this block, instead of kind of further propagating up the call chain, because we're inside a try block, we're now going to go to the catch clauses and see, is there a clause that can catch the particular exception that's been thrown? And if you look down below, the thing that we threw was a stood runtime error. So in this particular case, the thing that we're catching is a stood runtime error. So this will actually catch the exception. It's catching it by reference. So E inside this block here, E will refer to the by reference to the exception that was thrown. The runtime error type itself, it's these types that are provided by the library. They have very minimal functionality, but they have a member function called what, which allows you to query the string that was used when you created the exception. This string here gets stuck inside the exception object. It's basically a member of that data member internal to the type. And then down here, or up here, what we're doing is we're just printing the value of that string. So it's going to print out yikes. Of course, in the real world, you wouldn't want to use yikes for your error message. If you do that, well, you may have encountered this. I mean, I've had code crash and you get an error message like yikes, and you want to strangle someone when they do that, So don't do that. But this is just an example. So it's not meant to be any kind of real worldish code. Anyway, so what will happen is we'll print out yikes, and then we leave the catch block. And at this point, like the exception is all processed, everything continues running as normally. In this case, there is no more code in func1, so we would basically just return from func1 and everything goes on happily. But as long as the exception doesn't get caught, you basically keep getting ripped out of blocks and propagating sort of backward up the call chain until eventually someone catches the exception. If no one does, I mean, if this kept going and eventually we end up at main, and then we get ripped out of main, at that point, this is a fatal error. You've not caught the exception, but the language requires that if you throw an exception, there will be someone that will catch it. If it doesn't get caught, you end up with some kind of error message to the effect that, exception of type blah, 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 thrown and was not caught or something like that. Instead, terminate is called. Anyway, so that basically, so the last variable that what got destroyed was by here. And again, the important thing is, like, as we're leaving these blocks in the stack unwinding process, you don't complete executing what was in the block. Like, things stop dead in their tracks. So this is why using destructors to do cleanup is really important, because when you leave a block, the only thing you can rely on is the destructors are called. So if there's anything that you want to do in the failure case where there's an error, which typically what you want to do is clean up things, maybe deallocate some memory you had allocated and so on, close some files that are open, things like that. If you don't do it in a destructor, it won't happen. And then you leak the resources. And we'll look at this in more detail a bit later on. This is essentially what makes it difficult to write code that's correct with respect to exceptions. Sometimes what's called exception safe code. You want to make sure that when people start throwing exceptions, you don't start leaking resources like memory, open files, other things like that. Any questions? And there's another example here if you want to run through on your own, another example of stack unwinding. A little bit more about exceptions. They're what are called function try blocks. So you can wrap up an entire body of a function in this try block, which is the syntax that's being used here. This is just for illustrative purposes. We have like the main function. We're not putting the try block inside the body of main. Rather, what we're doing is we're putting the whole body of main inside of a try block. So immediately after here, we say try, and then the whole body of the function is essentially inside a try block. There's not really much benefit to using function try blocks for regular type functions like main or something like this. The reason for them to exist is for constructors and destructors. Because if we wanted to do something like this, we could just put the try block like right inside main, like everything inside the brace brackets for main. We just have try at the very beginning, and you kind of an end brace bracket down near the end, and we could catch any exception that was thrown inside main. But destructors and constructors are different stories because there's lots of stuff that happens outside of the brace brackets. And we need to be able to catch those exceptions sometimes. So it's really for the purpose of constructors and destructors we have this functionality. But nevertheless, we can do this for any function. It's just practically speaking less useful unless the function is a constructor or destructor. And before I get into like in more detail why it is useful for constructors and destructors, it's really important to understand what a constructor does and what a destructor does in the particular order in which things happen when you're constructing and destroying. So this is basically what this slide here is trying to kind of outline. We're going to assume there's no virtual base classes, which you're definitely not going to use in this course. They're kind of more rare thing, but occasionally useful. Assuming there's no virtual base classes, then the order that things happen in a constructor, when a constructor gets invoked, first, any non-virtual base classes get constructed. In other words, your base class objects get constructed. Then your non-static data members get constructed. The non-static ones are the ones that are on a per object basis. They're not like class-wide. And then after all that's done, and that can be a lot of work, like most of the work in a constructor probably doesn't happen between the brace brackets you write, but eventually it executes the constructor body you provide, which is basically what's between the brace brackets and the definition of the constructor. But there's lots of other stuff happening outside the brace brackets, and the issue becomes those things can throw exceptions. What happens if you want to catch the exceptions that are thrown when you're constructing a base class object or constructing a data member? It's too late to try to wrap the contents of the constructor inside a try block. So you put the whole constructor inside a try block. Destruction happens in the opposite order. So this is easy to remember as long as you can remember the order things are constructed, and destruction is the opposite order. So when you invoke a destructor, the first thing it does is executes the body of the destructor. In other words, what's between the brace brackets that you provide in the function definition. Then after that's done, it destroys each of the data members, but in reverse order. Here it's constructing them top to bottom in the class definition. Here it destroys them bottom to top. And then any base classes get destroyed in right to left order, whereas here they're left to right. So basically everything happens in exactly backwards order. And if you think about it more carefully, you kind of have to destroy things in the reverse order for construction. Otherwise, this could lead to other problems in the language. And as I mentioned in I think the last lecture, the lifetime of an object is deemed to begin at the point that the constructor successfully completes. So if an exception is thrown in a constructor, this is the lifetime of that object never starts, therefore the destructor is not called, meaning that if there's any cleanup you need to do, you better clean up before you leave that constructor, otherwise it won't happen. We're going to assume that just destructors don't throw. Like generally speaking, you never want to throw exceptions from a destructor because destructors are being invoked very frequently during stack unwinding, and if you throw an exception while you're processing an exception, this is not allowed, and your program will be terminated. So basically you don't want to throw in a destructor because it's just kind of begging the gods to punish you. And maybe one other thing I should say with respect to with constructors is even if you catch an exception in a constructor, the exception will be explicitly rethrown. Like in other words, if the constructor fails, there's not any way that you can kind of salvage things. That exception is going to get propagated to the person who's constructing the object because they need to know that the construction was not successful. Mm-hmm.
When you close the entire constructor in the try-catch block, does that also catch any exceptions in the initializer list?
Yeah, that will catch. Yeah, if you use a try block, and I'll go through an example in a moment. I think it's on maybe 2 slides later. This is the reason that you might want to use a try block for a constructor is that when you wrap the constructor in a try block, it's like all the stuff that's done by the constructor is protected by that try block. So if you're constructing a base class object or a data member, which is what would be kind of, well, I guess either could be the case for an initializer list. If anything throws, those exceptions would be caught. But the thing is, it doesn't change the fact the object will not ever be constructed. Like once things fail, like you're toast. So this is the reason why for constructors, even if you catch the exception and you say, I'm not going to rethrow it, the language will rethrow it for you. Like it's going to throw an exception to whoever called you regardless, like whoever is trying to create the object, because the compiler the language can't create it. So it can't not propagate the exception. Otherwise the person who's creating the object would incorrectly think it's been created and happily go along with an object that's not properly initialized. Any other questions? Okay, so let's look at a few examples here. So first, I just want to kind of make a little bit more concrete, like construction, destruction order, the things that happen, order in which things happen. So here I have a widget class, which is inheriting from the base class up above here. So this widget class has a bunch of data. Part of the data is coming from the data members down below here. So we have a data member S and a data member T. In addition, we have a base class object as well, which comes through inheritance. So basically, one of these objects is also going to be part of the data associated with the widget. And now what we're going to do down below here is we're actually going to create a widget, just default construct it. So when we try to default construct a widget, it's going to obviously invoke our default constructor for our widget that we've provided here. And the order in which things will happen is before it ever hits the opening brace of the widget constructor that we've provided here. In other words, before it hits the constructor body, lots of other stuff happens. The first thing that happens is any base class objects of this class get created. So there's one base class object, so it's going to construct a base object inside the widget. Then after that is done, it's going to construct the non-static data members from top to bottom in basically declaration order. So first, if we're reading the widget class definition from top to bottom, the first thing we hit that's non-static data member is s underscore, so it will get constructed. Then t underscore gets constructed. And then finally, after all that's done, then finally, we actually get to execute our constructor body. And this is, by the way, some people have been running into problems with const expert code where in the constructor, like they don't use an initializer list, and then inside the constructor body, like in the brace brackets, they correctly initialize the data members of the class. But the thing is, it's too late because they've already been initialized before you hit the brace bracket. Like all the data members will be initialized before you hit the brace bracket. It's just that if you don't initialize them, maybe they default initialize to not being initialized, and then you get an error. Anyway, so there's lots of reasons. This is like an off topic from what we're talking about here, but what I'm trying to convey is there's lots of important reasons to understand what's the mechanics of construction, what happens, because otherwise, if you hit an error, for example, in the const expert case I was talking about, you might be puzzling over the compiler error message for forever going, I initialized it. What are you complaining about? It was never not initialized, but it's not true. It was actually initialized before to nothing. Well, like literally nothing. It's uninitialized. Anyway, so that's the construction order. Then when we reach the end of the block in which W is defined here, when we hit the end of the block here, then it's going to be destroyed. So what happens for destruction? Well, everything happens in the reverse order. So first we start out by calling the destructor body, which is doing nothing in this case. And by the way, the constructor body in the previous case is not doing anything. So we're not actually doing any work at all in the constructor body, but lots of stuff happens when we construct and destroy objects. So in the destructor case, we're going to first execute the destructor body, which does absolutely nothing. Then we're going to destroy the data members from bottom to top order, like reverse order. So we destroy T first, and then S, and then we're going to destroy the base class object base. So this is the way things work. So basically, as long as you know the order things are constructed in, it's easy to figure out the destruction order because it's just backwards. So there's a lot of stuff going on here, and the issue becomes like, what happens if I want to, in the constructor, for example, what happens if I know that there can be an exception that can be thrown during construction, and it's construction of either the base class object or one of these data members here. If I put a try block inside the function here, this is not going to catch any exceptions that are thrown due to constructing base class objects or data members, because all these things are constructed before I ever go into this function in the first, like inside the body of the constructor to begin with. So this is what's special about constructors, and it's a similar issue with destructors. Like there's lots of stuff that happens outside of the body that you provide here. And what happens if you want to catch exceptions that happen outside of that body? Like overall, anywhere in the destruction process or anywhere in the construction process, if you want to catch an exception, how do you do this? This is when try blocks, function try blocks would be used, because they wrap the entire process of construction and destruction. So to give a more concrete example here, we have a gadget class which provides a default constructor which just throws. So this is not a very useful class. It just, every time you try to create an object, it just throws this, says, no, you can't do this. And it provides a destructor. And we have this widget class. It provides a default constructor and a destructor. And then we have some code down below here which is trying to create a widget. So if we look at what happens when the code executes, so main here is going to try to default construct a widget. So this is going to invoke the default constructor for widget. So the first thing the default constructor for widget is going to do is if there's any base class objects, it would first construct them. There's no inheritance here, so there are no base class objects, so nothing needs to happen here. Then it's going to construct from top to bottom order any of the non-static data members. So there's only one, G underscore, which is a gadget. So it's going to default construct this gadget, G underscore. So this is going to invoke this constructor, but this constructor throws. So if we didn't have do anything special here, we would not be able to catch the exception that's thrown here, because the point at which we're calling the constructor is before we actually hit the body of the constructor. So what we've done here is we've wrapped the entire body, the entire constructor in a function try block. So this try block is not inside our constructor body, right? There's no opening brace bracket before the try. So this try is like outside of the function body that we provide. And kind of the meaning or semantics of this is that it's kind of catching any exception that is thrown anywhere during the construction process. So when you're constructing base class objects or data members or or in the actual constructor body we provide. Anywhere something is thrown, it will catch it by this try block. So this is the kind of application in which you would use a function try block. For regular functions, it's not a big deal because you can always just put the try block like kind of inside the function that you're trying to protect. But in the case of constructors and destructors, because there are things that happen outside of the body that you provide, the function body, you need a way to be able to catch exceptions that happen in those cases as well. So in this case, what would happen is the exception that was thrown when we tried to construct this thing. So like basically anytime we try to default construct a widget, it's going to fail due to an exception being thrown when we construct the underlying gadget. So when it throws, what will happen is that this try block will catch it. This dot here is going to catch the exception. We're going to print out an error message. We're going to print out a message just saying that we're in the constructor body trying to create something. Here we're going to catch the exception and just print out a message saying there was an exception in the constructor. And this is automatically going to get rethrown. So like there's no way for us to stop this exception from propagating up to the person who's trying to construct the object. So whether we like it or not, this person here, the caller, is going to know that this widget was not constructed. But this is what we want, right? Because if we just silently failed, if this didn't continue to propagate the exception up to the person who was trying to construct the object, they would have no way to know the construction was not successful. So this is the reason why in the case of a constructor, even when you catch the exception, even if you don't rethrow it, it automatically gets rethrown. There's no way to stop that exception from being propagated up to the person who was trying to create the object in the first place. But again, this makes sense because they would need to know that it was not constructed successfully. Anyway, hopefully that gives you kind of an idea about function try blocks. Because sometimes you will want to catch exceptions that kind of happen anywhere in the construction process, and then you need to use a function try block. Any questions? Yep.
So would the private data members be constructed for the standard error messages or after, or like where in the try-catch block in the constructor does the actual initialization happen? Is it before or after the messages?
So like this is our constructor body is here. So like when we enter the constructor body, we're going to print out we're basically in the constructor body. But the difference is like we put this try in front of the actual body that we're providing for the constructor. So the meaning for this is that if any, not just if this body probably is less likely to throw an exception. But certainly the construction of this data member, we can say categorically, is always going to throw an exception. So if anything throws an exception, like even prior to entering this block, like either we're constructing base class objects or data members and it throws an exception, that because of this try being like it's outside of the constructor body, the meaning is like if anything throws anywhere, we catch it. And then we can have as many catch clauses as we want here. This will also catch anything that's thrown in the constructor by itself. Like anything that throws anywhere will get caught by this. But the kind of the order that things would happen in, I guess, is that, let's see, so we're going to, if we kind of walk through this, when we try to create the widget, it will call the default constructor for the widget. So the first thing that happens, we try to create base class objects. There aren't any, we're done. Then we try to create the non-static data members. There's one. We try to create this. This is going to try to call the default constructor for gadget. This throws. So I guess this would probably, I think this wouldn't print a message. We'll just get ripped out of the try block. We'll go on to the catch. We'll say there's an exception in the constructor, and then then it will rethrow the exception. So I believe it would be the case. It wouldn't print anything in this particular case because it never gets to the constructor body. Any other questions? Yeah.
If you in the catch block throw a new exception, will that be the one that's propagated up instead of the one that was originally thrown?
Yeah. Let me think about this. Yeah, I believe that once you're in a catch block, I think you can. It's not. I think it's deemed to be like it wouldn't be actually deemed to be. You're still processing the exception, and then you're throwing an exception while processing one. I think at that point it would be okay. I'm honestly not 100% sure, but I think that's the case. Is that what you're asking? Okay. It's a good question. There's lots of kind of fine details in the language, and to be honest, there's certainly lots of things that even I don't know. Any other questions? Okay, so let's go on here. So there's a few other additional examples. Again, some of them, the slides I'm skipping, it's not because it's not really stuff you're responsible for. It's just there's kind of more examples than we have time for. A lot of them are still related to stuff we've covered. So you might still find some of those slides to be helpful. And at some point, I will post a list of like the slides we've covered, because some people are saying it's maybe hard to keep track of what we're doing because sometimes we jump around in the slides. So I'll post that at some point, or maybe progressively put a list together as the course proceeds. Anyway, the next thing I want to talk about is the noexcept specifier. So what this allows us to do is we can attach to functions a statement to the compiler telling it, like, is it possible that this function might throw an exception, or we can categorically say, no, it won't throw an exception. So when we're declaring functions, we can say things like, for example, noexcept false. Noexcept it takes basically something that's either true or false, like something that's a constant expression and evaluates the true or false. And if it's true, this is saying noexcept true is saying it's true, I don't throw exceptions. So if I say noexcept true, this is basically saying the function func3 is guaranteed never under any circumstances will it ever throw an exception. Whereas this case here, func2, we're saying noexcept false, so this is saying it's not true that I won't throw exceptions. So in other words, I may throw exceptions. It doesn't mean that you definitely will, but you might. You have the right to throw exceptions if you feel like it. If you don't specify anything at all, it's the same as saying noexcept false. If I don't say anything, I might throw. So if you want to say you're not throwing, you have to say noexcept false, essentially, or just noexcept. And the reason why it may be helpful to do something like this is effectively it allows the compiler to make optimizations it couldn't otherwise make, because when you have code that may throw exceptions, you don't see it yourself typically, unless you're doing things like I mentioned in the previous lecture. I think if you're doing like code coverage and you have branch coverage turned on, and then you go, oh my gosh, there's all these branches in the code, but I look in the source code, there's not really branches there. Well, there are branches there. It's just that they've been introduced to handle all those special cases, like if this function returned because an exception was thrown, do this, else do this. So there's a lot of extra control flow introduced. But the compiler, it costs you something to have that control flow there. But if you know an exception won't be thrown, why put any of that code there? Because you know the exception, like the code will never emit an exception. So this is one of the reasons why having something like this functionality in the language is very useful. For example, it can allow the compiler to omit code that otherwise it would be obligated to have there, just in case you might throw an exception. It's not code that you write yourself, but again, it's there. It doesn't change the fact it costs you something to run the code, like to run those CPU instructions and so on. Anyway, so this is the basic idea. And because it can be any constant expression that's in like that's the parameter that's provided to noexcept here, we can also do things like, for example, maybe we'll want to say that this function func5, which is a template, so there's some template type parameter t, depending on the size of t, this may or may not throw an exception. So we're saying like, this is guaranteed not to throw an exception as long as the size of t is less than or equal to 4. For some reason, maybe if t is bigger, we may have to allocate memory, and then we can't guarantee that an exception won't be thrown, because if we run out of memory, maybe we have to throw an exception to signal that to the person who called us. So you can basically, size of t is a constant expression because the compiler knows at compile time what the size of the type is. If it didn't, it would have problems generating code for that type. And is there anything else I want to say for this slide? I think that covers it. Any questions? Sorry, yeah.
Sorry to miss this, but if you put noexcept on something that could throw an exception, is it just silence the exception, or does it give you a compiler?
If you put, well, the compiler, often it'd be very difficult for the compiler to know for sure whether something might actually throw an exception, because you could have, assuming that you have, like, you can't statically just by looking at the code see it's going to throw. Like if you function a single line throw, well, you know it's going to throw no matter what. But it would be difficult in a more complicated function. Maybe you have like if and then throw. Like the throw is inside an if. The compiler might have a hard time to know, like, yes, you have an if there, but maybe that if never can get hit. Like you'll never actually take if the condition for the if is never true, therefore you never throw, even though there is a throw statement in the function. So it may be difficult for the compiler to tell, except in kind of very trivial cases, like you have something like one line in the function, which is a throw statement. But it doesn't matter, even if you have one line, which is a throw statement, you can still stupidly say noexcept. But you better not call it function, because bad things will happen if you call a function that's marked noexcept and it throws. But this is kind of getting a little bit ahead, because actually I think the next slide or subsequent slide is going to talk about the issue about what happens if you throw inside a noexcept function, which you're not allowed to do. Did that answer your question? Okay. Okay, I think it's maybe one slide after this, but definitely we're going to talk about that in a moment. So just a few things about this noexcept specifier. So it's part of the function's type, but it's not part of the function's signature. The signature is just like the name of the function. So if you have a function defined twice with the same signature, it's multiple definitions, which you're not allowed to do. So for example, if I try to define a function f, and this without the noexcept, or basically saying the function f, it returns a void, it takes no parameters, and by the way, it might throw exceptions. Whereas this line here, we'd be saying kind of the same thing, except this function doesn't throw exceptions. However, if we wrote code like this is invalid, because what we're doing is we're defining the function f twice. This is why it's important that the noexcept part of the function, although it's part of the type of the function, but it's not part of the name of the function, it's signature. So if you have two functions and they differ only in the noexceptedness, they're the same function, therefore you have multiple definitions. So basically you can't overload on noexcept, because this would lead to multiple definitions of the same function. But you can't overload because it's not part of the, anyway, enough said about that, otherwise I'm going to just overly complicate things. Any questions? Do I want to quickly comment on this? Not really, since we're running a little bit behind. That was sort of an optional slide to discuss. This comes back to the question that was asked by the student near the front. So if you have a function where it's making the promise not to throw exceptions, so either you said noexcept true, or you just said noexcept. If you say noexcept without any like parameter, it's the same as saying true. So either you say something like noexcept or noexcept true. This function here, if it's ever called, will terminate the program. So like obviously this function categorically, if it's called, it will throw an exception, right? Because there's one line, there's no if condition, it will throw. But we've said that this function doesn't throw. And if you throw in a function that doesn't throw, it is told, or promising that it won't throw, this is a fatal error. And your program will be terminated by the runtime. So I guess if you, for some reason, you really wanted to terminate the program, I guess that would be one way to do it, although there's probably better ways, maybe call std-abort or something like that. Anyway, so you have to take noexcept seriously, because if you label a function noexcept, and well, maybe I do actually throw, you're in big trouble if you actually do throw. And part of the reason why, you kind of reason that if you did this, if you say it's noexcept and then you do throw, you can imagine it's going to cause big problems, right? Because when you say noexcept, the compiler can now say, well, this won't throw. So all the code that I could put in, because when you call this function, if it could throw, there would be like extra logic that the compiler introduces to say, like in the caller saying, if I return because an exception was thrown, do this, else do this. Like basically the compiler has to introduce code kind of like this everywhere where you call something that could throw. There's two paths by which you can return. I'm kind of maybe oversimplifying things, but you can kind of think of it this way. And if you say noexcept, then what you're saying to the compiler is like, I won't throw any exceptions. So the compiler can then say, well, all this extra code that I would generate to handle the case of it throwing, not throwing, I don't need it because it's never going to throw. So it takes all this code that's critical for exception handling out, and then you throw, and now it needs it, but the code's not there because it didn't generate it because you said it won't be needed. So like you can kind of reason like it would have no choice but to somehow abruptly terminate your program because the code to actually handle the exception that you just threw is probably not there because the compiler probably just optimized it out because you said you don't need it. Anyway, so you have to take noexcept very seriously. Don't put it in unless you really know that you're not going to throw exceptions. And in practice, it's often very difficult to know that you can say a markup function is noexcept. The reason why is that, like I often hear people saying, like, if you're not throwing exceptions, mark it noexcept. Just that's the only logic involved. Not more thinking than that. But I think this is a big mistake. Like this is getting overly ambitious for marking functions noexcept, because the problem is if you have some code and you look at it, well, today it's not throwing exception. In the real world, though, there's more than just today. Today is like a very small piece of the life cycle of the software. Some later point, you have version 2, version 3, version 4, and you add more of these things called features. You add more functionality. And maybe at some later point, due to functionality you add, it becomes necessary because the code gets more complicated. Now it has to throw. Before it didn't. In version 1, it didn't have to throw because you're doing very simple stuff. You add more features. Then in version 2, now it has to throw. And now you go, oh gosh, now I need to take away the noexcept. But if you take away the noexcept that you had in there, now you break everyone that's calling that function because they were not expecting it to throw exceptions. You didn't have a noexcept there when they were using that function, writing the code that calls it. So they go, it's not going to throw, don't need to catch, don't need a try block. Then you take that away in version 2, and then everyone who's using your code potentially breaks. Because when you throw an exception, you know they're not going to have the code to handle it because you told them before in version 1 it doesn't throw. Question?
Could a noexcept function have a error like an exception thrown in it as long as it happens within a try-catch block within that function? Okay,
yeah, so maybe I should, yeah. It's a good question. Like a lot of people get very sloppy when they're talking about like functions throwing exceptions. Like to be maybe split hairs a little bit more, and it's important to split the hair so that people understand what the issues is involved. When we're talking about like throwing exceptions, usually what we really mean is the function's emitting an exception. Like, in other words, you could have a function that internally is throwing all over the place. It calls other functions that are throwing, but there's try blocks that catch everything. So that function never propagates an exception out to the person who called it. So like when we say noexcept here for this function die, the promise that's being made is that die will not let an exception propagate out of it to the caller. However, it's not making any promise. Like you could write this in a different way where get rid of the throw zero. Instead, what you have is this function calls another function, and then that one throws, but the die has that wrapped in a try block, and then it catches the exception. So there's internally could be exceptions going on, maybe lots of them, but they're all caught and they never propagate out of die. Then this would be okay. This would not cause any problems with respect to the noexcept that we put there. But in this case, we're throwing an exception, we're not catching it, therefore it's propagating out of this function. This violates the noexcept part of the promise that's being made here. Noexcept is saying, to kind of be more precise, I will not let exceptions propagate out of me. I will not emit exceptions. But internally I can do whatever I want. This is none of your business. Like as long as I don't let exceptions come out, you don't have to worry about catching them and dealing with them. So from an interface point of view, like API point of view, all it really matters is what are the exceptions I propagate out to you? Because those are the ones you have to catch and deal with. The ones that I use internally, you never see them anyway. It's an implementation detail. Does that answer your question? It's a very good question. So again, when we're talking about noexcept, like usually what we're talking about is the function is not going to emit an exception. It won't propagate out, but internally it can do whatever it wants. And yeah, I think that's all I want to say about this. I guess just coming back to the last bullet, like again, it's very difficult in practice to mark things as noexcept, because if you know that there's going to be like an evolution of the software over time, and there's going to be version 1, version 2, version 3, it's hard to look into your crystal ball and say, there is never any circumstance under which any user or customer could ever ask me to add a feature to my software where this function I can categorically guarantee will never need to throw exceptions in version 1 or any future version of the software. It's often very hard to do. Because like all of a sudden you start using a new type because you have to add the feature, and then that particular type can throw exceptions. You have no choice. Then the function needs to be able to throw. So it's in practice, it's a very difficult guarantee to make. So I'm a little bit, it makes me a little bit nervous when I see people kind of suggesting just if it doesn't throw, just make it noexcept. I would go kind of the other way. Unless you absolutely are certain there's no way in heck that it could ever throw in this version or any future version, don't mark it noexcept. Otherwise you could end up regretting your choice later. Because when it's always kind of safe to add, it's probably always safe in practice to add a noexcept, because you're just making things more restrictive. But if you drop the noexcept, this will impact other people who are using your library, because now you can throw exceptions that they weren't expecting. Any other questions before we continue here? Okay. I just want to talk a little bit about exceptions and function calls, because there's some situations where exceptions can be thrown that maybe you might not think about. And just so that you basically don't get tripped up by some of these issues and have exceptions happening in places where you don't want them to be happening, it's worthwhile to make some comments in this regard. So basically what I have on this slide here is just a very simple, a few lines of code here where T is some class type, and it's like non-reference type. So basically we're passing by value, returning by value here with this function func. And it's been marked noexcept, and well, I've just left it as some expression. Maybe it's noexcept true, maybe it's noexcept false. We're default constructing an x, and then we're calling this function func, passing x into the function, and then taking the return value and using it to construct another object of type t called y. Basically, what's happening here, there's like a pass by value happening, return by value happening. Both of these things fundamentally involve copying. Because the way that you get this parameter x into the function func is you copy x into the local variable, the formal parameter of the function. So this has to be done by a copying operation. And when func returns, because func is returning by value, you have to propagate the return value out of the function, which requires a copy as well. I mean, these could be elided, but at least kind of conceptually, there's copying involved. If there's copying involved, then there's a possibility, at least if the copy is not elided so that it's not happening. Well, how does copying happen? Well, it happens either through a copy constructor, move constructor. Well, they're code, they can throw. So then the whole issue here becomes, you have to be careful, for example, when you're passing by value or returning by value, because the act of passing the value, returning the value back, or passing the value into a function could result in an exception being thrown, because you could have a copy constructor, for example, that throws, and this is not uncommon to have. So we need to be a little bit careful. So the kind of the main point really that this slide is trying to convey is when you're calling a function, the actual mechanics of calling the function and returning from the function can throw exceptions due either to parameter passing, where you're passing by value, or by from the return statement when you're returning by value. And in this regard, it's important to know sort of which of these copy operations is deemed to be owned by what part of the code. So for example, when I'm passing a value into the function and I'm using a copy to do this, who's deemed to be doing the copying? Is it the person who's calling the function, like the caller, or is it the person who's being called? For parameter passing, it's the person who's calling the function, the caller, who's deemed to be doing that copy. In the case of returning a value back from the function that's being called, the copy that's doing that is deemed to belong to the function that was called. The reason why this is important is when you're trying to decide, well, can I mark this function noexcept or not? Depending on who is deemed to be doing this copying, you may or may not need to worry about whether it can throw an exception. So for example, in the case of passing by value, if an exception might be thrown due to passing by value, it doesn't have any impact on the no acceptedness of the function because the passing the parameter into the function is done by the caller. So if it throws, it's the caller that's throwing, it's not the function. So you wouldn't be violating the no except if you mark this as a no except function. On the other hand, if you're returning by value and you know because of the way you wrote the function that a copy either is not elided or not guaranteed to be elided, then you have to worry about could that throw an exception doing the copy to propagate the value back, either a copy or a move. And if you know you're either doing a copy or a move and can't be sure that copy or move won't throw an exception, then you would have a problem if you mark this function no except, because although maybe nothing in the body of the function throws an exception, the thing is, or anything other than the return statement throws an exception, because the return statement may require a copy constructor, a move constructor to be invoked, and because that copy operation is deemed to be done as part of the function that's been called, this means that if that copy operation did throw, or move operation did throw, this would mean that the function which promised not to throw exceptions is throwing. So this is why it's important to understand who is deemed to be the person who's doing the copying. Is it the caller or the callee with respect to passing values in and propagating values back out? Because if you don't understand this, then you might unknowingly violate the no except contract that you're promising. Anyway, so that's some issues with respect to function calls. And so if you want to try to avoid some of these issues, for example, if you're passing parameters into a function and you just can't accept any possibility that there might be an exception thrown, then maybe don't pass by value, pass by reference. Then there's no copy made ever, and that way you can be sure that there's not going to be an exception thrown due to the process of copying, which maybe invokes a copy or move constructor throwing an exception. Another solution to the problem is you still pass by value, but you make sure that the copy or move constructor that might get used is a no except function so that it's not going to throw. That would be another way to deal with this problem. Or another even better solution is maybe just make sure it doesn't copy. In other words, write your code so that copy elision is guaranteed. And in this case, because you know the copy can't happen, there's no possibility it can cause an exception to be thrown because it doesn't happen in the first place. But sometimes the second two bullets are not, like the bullet 2 and bullet 3 maybe are things that are maybe harder to guarantee sometimes. So sometimes the only solution is just pass by reference, and then you can't have an exception thrown.
So when an exception happens, it's something that's constructed with the copulation. That means it happens in the caller.
Sorry, did you say if there's copulation? Because if the copy is elided, then there's nothing that can throw because no code is going to be invoked. We only have to worry about whether a copy or move could throw if it actually is going to copy or move. So copulation is kind of the great thing. It solves a lot of problems. It solves this. If we know the copy is always elided, then we know that nothing can throw because there is no copy. Because it's what we're concerned with is there a copy or move operation which is being done basically by a copy or move constructor, but there's no rule in the language that says a copy constructor can't throw. Sure, they can throw. A move constructor, they can throw too. As a general rule, usually you try to write move constructors so they don't throw. And often, for most types, you can do that in a way that they won't, because usually you reuse resources when you do a move. So usually the thing that can throw is you try to allocate a resource and it fails. So moves you can usually get away without doing you can get away with guaranteeing that it won't throw. But copying is typically very problematic for most types. So often copies can't be guaranteed not to throw. Anyway, but I think if I understood correctly, you were saying like the case where copulation is happening. If it is happening, then there's not an issue then?
Or no, the question is asking, so if copulation happens, then the thing you're constructing throws an exception. Does that happen as a caller or a callee?
Like the only thing that's at issue here is just the act of any copy or move that's required to propagate a return value from the callee back to the caller, or kind of the converse problem, which is you have an argument in the caller that you're trying to propagate into the callee. Either because you're in the first case you're returning by value, in the other case you're calling by value, which requires a copy. But like everything else is kind of not within the context of what we're talking about here. Like it doesn't really matter. If you're throwing for other reasons, like all the same rules would apply. Like if you know that you might throw for other reasons, then you don't want to mark the function noexcept, because then you know you could violate it. But really what I'm concerned with more here is that maybe you think that the function can't throw because like you haven't put any throw statements anywhere, but what you've forgotten is your function returns by value. And maybe if copulation isn't required, that means that the way that the value gets propagated out of the function is either by a call or a move. And what happens if the function that you're using, the call and move constructor, what happens if it can throw? Then what happens is you kind of get blindsided. You'll maybe realize this issue. You write the function saying noexcept, but actually it can throw because the constructor that you're using to propagate the return value back can throw. And because that's deemed to be part of the function's code, it means that function is throwing an exception. But what you're talking about is more like what's happening in the body of the function itself, like not the part that's the mechanism of getting return value back. And if you write your code in that way, then it's probably more likely you would go, oh, I'm throwing, well, I can't mark this noexcept. But this is kind of a more subtle issue you might overlook, which is that I'm not throwing anywhere in my code, but somehow magically it's causing an exception to be thrown sometimes. So this is kind of a more subtle issue, which is why I'm covering this. Did I answer your question?
Yeah.
Okay. Any other questions? Okay. There's the similar problem if you're trying to return by value. So if you want to return by value, one way to avoid the possibility of exceptions being thrown, you can make sure that the copy or move constructor for the type that you're using, if this is feasible, you can make sure that it makes the promise not to throw. And most move constructors usually make the promise that they don't. Oh, sorry, we're going way over time. Oh wait, that clock doesn't match my watch. Oh, anyway. I think we are over time, so I better stop here for today. Sorry about that.